Greetings, computer nerds. I'm here to give you a little update on the Relay2Tetris computer project. Since one of the goals of the project is to provide a sort of standard set of relay boards that anyone can use to build their own computer, I thought I'd take a little time and show you some of the general features that all the boards share. In the bottom left corner of the board, we have two separate power inputs. One of them can be pushed through a voltage regulator, and either of them can be connected to power either the board's relays or the output of the board. All of the various board options can be selected using solder jumpers. The four IDC connectors on the bottom of the board provide access to a control bus, two data input buses, and an output bus. In the unlikely event that the input data line's voltage needs to be adjusted down, they can be routed through resistors before going into the first functional unit. However, almost always, the inputs can be directly fed into the first functional unit using solder jumpers on the reverse of the board. A small patch panel allows you to select which control lines control which functions of the board. The board control relays are located next to the patch panel. If a signal is always on or off, you can just set its state with solder jumpers. And of course, along the top of the board is a whole bunch of LEDs that let you know what the state of the board actually is. The register board shown here has three separate functional units. The first is an input multiplexer that lets you choose which of the two data input buses will be presented to the register. The register itself stores 16 bits of data. In order to update the register, you first have to raise the enable control signal. When enable is raised, the board becomes responsive to the set and clear control signals. The bits in the register are self-latching. Once they are set, they stay set. Raising the clear signal, however, disables this function. If you just raise enable and clear, the register will reset to 0. The set signal gates the output of the multiplexer into the register. Since all the bits are self-latching, if you just raise enable and set, the register will become the OR of the register's contents and the input data. But if you raise all three control signals, then the register's contents will be replaced by the output of the multiplexer. The update sequence that I use is to raise enable, set, and clear in the first tick, and then drop clear in the second tick, before finally dropping the other two signals. This ensures that the data is securely latched into the register. Finally, for convenience, there's also a reset control signal. This just clears the register to all zeros. The third part of this board is the bit test unit. This is completely configurable by solder jumpers and allows you to check for two completely different bit patterns. On this test board, I have it configured to detect 0, -1, and using the yellow jumper wire, it also detects less than 0. There's even a couple of extra breadboard relay locations that you can use to add extra logical functions. Even though the data buses are nominally 16 bits wide, I'm using 20-wire IDC connectors, which means the top four lines are conveniently available to carry these extra bits of data. And there are header pins that make it easy to hook them up. Now here's the board hooked up to a Raspberry Pi and running a test routine. The Zeus Adder is my favorite board. It's just so ridiculously cool. A normal adder suffers from something called carry propagation delay. In a normal adder, each bit has 3 inputs, A, B, and carry, and generates 2 outputs, the sum and the carry out. This means that you can't generate the output of a bit until you get the carry out from the previous bit. In a Zeus adder, on the other hand, there's an extra input called not carry in and an extra output called not carry out. The relays themselves are only controlled by the A and B input bits. The carry in and not carry in signals, along with another signal that's always on, bounce around the relays and eventually end up in the output, carry out, and not carry out bits. I've tried to document how it works on the GitHub page, but I must warn you that trying to understand how the Zeus adder works will make your brain hurt. Now, once you have a Zeus adder working, you can start doing some cute tricks. Normally, the input to the first bit has not carry set to true and carry set to false. However, if you reverse this, you get an adder that adds A plus B and then adds 1 to it. Conveniently enough, A minus B is equal to A plus not B plus 1. So by simply adding some relays that can negate B, we can also do subtractions. Also, if you just want to do a fixed adder, you don't need the relays that are controlled by the B inputs. For example, this board is a fixed 8-bit incrementer that will be used in the program counter logic. Finally, the board can be configured not just as a single 16-bit adder, but as multiple shorter adders. And you can extract the overflow carry from each adder. Okay, here's the Zeus adder and the incrementer in operation. Moving on, here's the logic unit board. This device is wired to compute both the exclusive OR and the AND of the inputs. Those circuit paths, if energized, are then ORed together and fed into a NOT unit. The result is that the board can compute all 6 of the Boolean logic functions: AND, exclusive OR, NAND, NOR, and XNOR. It can also compute the completely useless Boolean functions true and false. The unused space of the board is configured as a breadboard you can use to implement any function you want. And finally, we have the multiplexer NOT breadboard. I built this board because it can conveniently perform 2 functions that are required for the ALU. Each of the 2 ALU inputs can be optionally zeroed and then negated. And if you set one of the multiplexer inputs to 0, then it can be used to do the zeroing function. The rest of the board area is used for a relay breadboard. And the 2 rows of relays above the NOT unit can be conveniently jumpered so that they are controlled by the NOT outputs. Well, now I have the designs for all the boards I need to build my ALU. Wish me luck as I enter the hell of perpetual surface mount soldering.